Okay, hello. This is a hopefully fairly quick video on an explanation of problem set number 3. Let's take a look at question 1. So in question 1, we are asked to think about the kinetics of an allosteric enzyme. Just to refresh your memory, we have talked about two types of allosteric enzymes. For example, if we have an enzyme that has its active site, there is a small allosteric site away from the active site to where an effector, I will call it A, can bind to and basically affect how this active site is going to behave for its substrate. So the active site will either become nice and opened up, ready for its substrate, or it will change and be a little more closed off, and its substrate will not be able to bind to it. So when we talk about allostery, we talk about the concept of the behavior of the enzymes or proteins' active site or binding site being changed because of an effector molecule. Now, in the next scenario that we discussed, in the scenario of hemoglobin, hemoglobin is a 4 subunit protein, tetrameric. Its effector was its substrate as well. So its effector is actually O2. So in this case, like we discussed in discussion, the binding behavior of each subunit within hemoglobin is going to change depending on how much oxygen there is. And it's going to change in this way. If one molecule of oxygen binds to one subunit, and this subunit is saturated, the next subunit will become even more likely to bind to oxygen. Now, when these two are bound to oxygen, the third one will become more likely to bind, and the fourth one will be more likely to bind afterwards. So both of these moieties, so enzyme and protein, will show us an allosteric kinetics curve that will look differently than the Michaelis-Menten curve. Let's take a look over at this graph, and here I will show you what the kinetics graph of an enzyme that follows Michaelis-Menten rules would look like. It would probably look like this, right? And we call this a rectangular hyperbola. But over here we see that we have this sigmoidal curve, sigmoidal looking like an S shape, and this shows us that there is some kind of allostery going on with the enzyme that we are looking at, and it's telling us that we're looking at an enzyme. So hopefully that sets you up for this question. So it asks us that we know that allosteric effectors will change the concentration of substrate at which the enzyme reaches its half Vmax. So basically it's telling us that for allosteric enzymes or enzymes that will display allostery due to allosteric effectors or molecules, these enzymes will not have a Km, meaning that they will not have a constant number, constant concentration of substrate that will always basically show us how the allosteric enzyme behaves. So Km is not going to exist for allosteric enzymes because that number that would be Km is not going to be constant, right? It's not going to be constant. In class or in discussion, we were talking about, oh, there is a Km, but it just varies. But now that I'm thinking about it, it makes no sense, right? So Km within itself is a constant. And for us to say that Km exists, but it varies, that makes no sense, because how can something be constant and varied at the same time? So we will move on by saying that enzymes that behave allosterically do not have a Km, whereas enzymes or proteins that bind to their ligands that follow Michaelis-Menten kinetics will have a Km. Okay, now that that's settled, let's move on. On this graph, draw the approximate curves, so you don't need to be very exact, for an enzyme kinetics that has an allosteric activator in the mix, so an allosteric activator is present, and label this with positive, so the enzyme activity is being activated. And I will go ahead and draw that curve here. It's going to be up at the top, so it would look like this. Let me go ahead and put an actual line there. So that's going to be the kinetics graph that shows us how this enzyme is being affected by an activator. And then let's take a look at the graph that shows us allosteric inhibitor, and I will do that in blue, and that will look something like this. And we will denote that as negative. And that was an ugly circle. And how do we know that that was even uglier? And how do we know that this is correct? Let's take a look at some concentration of substrate. Let's say we take a concentration of substrate over here. If we go up, we see that the enzyme without any effectors around will have its Vmax, half of Vmax somewhere here, whereas the enzyme that has an activator present will have its Vmax, half of Vmax somewhere here, or its rate at which the enzyme is catalyzing the reaction, whereas the one that has an inhibitor is going to be over here. And this just goes ahead and supports the statement that allosteric effectors will change the concentration of substrate at which the enzyme reaches its half of Vmax, meaning that allosteric effectors do not have a Km. Okay, so that's for number one. Let's take a look at number two. Now, remembering everything that we just talked about regarding allosteric enzymes, let's look at which ones are correct. So A says at a given concentration of S, allosteric enzymes have the same V naught, so same rate or same velocity. And that is simply not true because we just looked at it in this example. If we take the concentration here, the rate is here for the inhibited enzyme, the rate is here for the control enzyme, and the rate is way up here for the activated enzyme. So A is incorrect. Allosteric enzymes have a Km. Km is a constant concentration of substrate at which half of Vmax is reached, so 1/2 Vmax. I did that wrong, sorry. 1/2 Vmax is reached. And just as we said previously for question number one, the concentration of substrate at which half of Vmax is reached will not be constant. So allosteric enzymes do not have a Km. So B is also out the window. Let's take a look at C. Ultimately, allosteric effectors change the shape of the enzyme's active site. That would be correct, referring to this example up at the left. Letter D, allosteric effectors can bind to a part of a protein distant from its active site. That is also correct, again pertaining to this example. Allosteric effectors do not need to interact directly, form electrostatic interactions with substrates or products. That is true as well. Again, if an effector denoted as A over here binds to an allosteric site and changes the active site, the effector itself has nothing to do with interacting with the substrate. All it does is it attaches to another allosteric site and changes the shape of the active site. So E is also correct. Let me go ahead and put some circles here. So C is correct, D is correct, E is correct. Allosteric effectors form non-covalent bonds with the enzyme they regulate. The key here is non-covalent bonds, which is an umbrella term for electrostatic interactions, hydrogen bonds, other types of interactions that are not coming to mind right now. And this would be correct because if in metabolism in the cell, we had inhibitors or activators that would bind to the protein or enzyme covalently. That would be really bad because it would mean that some proteins or enzymes will be forever inhibited or forever activated and would require another enzyme to kind of get off that covalently bound effector, and that's just not efficient. So it is correct that all of these effectors form non-covalent bonds because it's just so much easier to regulate that way and have them dissociate and bind whenever needed. Okay, let's take a look at G. Allosteric effectors change the delta G double knot of the reaction they catalyze. And this is not true because the allosteric effectors will only affect the affinity of the active site to the substrate because they will physically change the active site, allowing for the rate of the reaction to be changed, but not the extent of the reaction. So the actual concentration of product versus reactant will not be changed, meaning that delta G prime naught will not be changed. Rather, the kinetics or the rate of the reaction will be changed. So G is incorrect. Let's take a look at H and I. Allosteric inhibitors reduce the amount of product created by an enzyme over time, and allosteric activators increase the amount of product created by an enzyme over time. Now, at least in my section, there was some confusion between these two, and I think the confusion stemmed from this part of the statement. Products created by an enzyme over time. If we look at that term, or if we look at that statement as in a mathematical way, it would be products created by an enzyme over time. And this ratio, what does it remind you of? Rate, right? It reminds you of something being done over an amount of time or over a given amount of time. So this part of the statement for H and I is actually talking about the rate. So do not confuse it with thermodynamics. This is talking about kinetics. And exactly, and both of these are true. Allosteric inhibitors will reduce the rate of the reaction or the rate of products being produced, which is basically, the result of the reaction, if it's producing products. And the allosteric activators will increase the rate of the reaction. So both H and I will be correct. Okay, let's move on to 3 and 4. These are free response, and we're looking for, meaningful answers that make sense to you and make sense in terms of the question. So I will not dive too deeply into it, but let's just talk about it a little bit. So question 3 is asking, in as little possible jargon, explain how allostery helps metabolism to achieve homeostasis, maintain metabolite concentrations. Charismate mutase is a helpful example. So I like to think about this question by substituting homeostasis with the word regulation or regulate. Because when you do that, you really, at least in my mind, I understand what this question is asking. It's basically asking, when there's allostery, when there's some sort of regulation taking place in metabolism, how is this better for the cell? And there is a great example with charismate mutase, where we have, I think it was, hopefully I do this well off of memory, but we had charismate turning with through charismate mutase or catalyzed by charismate mutase turning into prephenate, and it eventually turns into tyrosine, which I can't remember. I think it was an inhibitor. You definitely want to check this, fact check this. And then if that reaction isn't happening, then charismate turns into tryptophan. And I believe this was an activator of charismate mutase. And So basically what happens here is charismate mutase is the enzyme that turns charismate into prephenate. Now, when there's a lot of prephenate, this will inevitably turn into tyrosine because this is how the pathway is. And if there's a lot of charismate mutase, if there's a lot of charismate and charismate mutase is not particularly active, then charismate will be sort of shuttled into turning into tryptophan. Now, let's say we're starting this concept, this question, from the fact that there's a lot of tryptophan. Let's just say that's our starting point. There's a lot of tryptophan. If there's a lot of tryptophan and it's an activator of charismate mutase, then it will activate charismate mutase, pushing whatever amounts of charismate there are this way, turning it into prephenate, then finally turning it into tyrosine. So tyrosine levels begin to increase over time because this activator is activating charismate mutase. Now, when there's significant amount of tyrosine, tyrosine is an inhibitor of charismate mutase. So tyrosine itself will go back and inhibit charismate mutase, telling it to stop doing this reaction. When charismate mutase decreases this reaction, so not a lot of prephenate is being used and not a lot of charismate is being is going this way into prephenate, charismate will begin to turn into tryptophan. And so you see how now the concentration of tryptophan rises and eventually tyrosine will go down. So this whole activator, inhibitor system of allosterically affecting charismate mutase becomes a way to balance out the concentrations of tryptophan and tyrosine within this cell or within this pathway. So this is how we reach regulation, or in other terms, homeostasis. So this is the type of meaningful answer, or if you have anything else to add, please go ahead. This is not the one and correct answer. This is just how I thought about it. And now let's think about question number 4. It could be a little connected to question number 3 in terms of when allostery is important. And there is a good hint here: if all enzymes operated at their Vmax at all times, so every single enzyme in a cell operated at its Vmax, meaning that per given amount of time, they were producing the highest possible amount of products. Then over time, if we're thinking in extreme ways in my mind, almost all reactions would run out of reactants, right? And that's not a realistic way of thinking about it. It's just, if we think about it black and white, then if every enzyme is working at its Vmax, a lot of product will be formed. And if there's no allostery, if there's no sort of negative feedback to tell these enzymes to calm down and not work at their Vmax, then delta G will over time change as well, because if we change the concentration of products over reactants, that will affect delta G. Okay, so that's sort of what we want you to think about for number 4, and anything else that I didn't mention but you want to mention. Question number 5 talks about the electron transport chain and the reduction potential. So let's take a look. If you are an exobiologist on planet X and you discover an organism with an electron transport chain, you go ahead and you isolate the redox compounds involved in this electron transport chain and determine their reduction potentials experimentally. You find 4 of them and you have the E prime naught of each. How will you, basically what this is asking, how will you determine the order of these compounds in the electron transport chain? So let's give you this hypothetical electron transport chain. Let's say we have 1, then electrons will be going to another one, then electrons will be going to another one, and another one. I start to sound like DJ Khaled by there's another one. But basically, let's just say there's this hypothetical electron transport chain, and we're trying to figure out which reduction or which redox reaction will go where in this order. And the way you want to think about it is this. For electrons to want to move in this direction, because in the actual electron transport chain, they do, right? They move from complex 1 to complex 4, and then finally to molecular oxygen to form water. How are electrons going to move this way with the least amount of energy being used in that process? They will move this way if the reduction potential of the next compound is higher and more positive than this one. And how does that make sense? If a compound or an element has an E prime naught, so a reduction potential that is large and positive, then this compound will really, really, really want to be reduced. That is my very simplistic way of explaining that the compounds or molecules that have an E prime naught of a large positive value, they are wanting to be reduced more than another compound that has a less positive E prime naught. If you remember that, this will solve all of your problems with questions like these. Because if you think about it, if we want electrons to move from this compound to this compound, or this complex to this complex, then this complex needs to have an electron potential that is more positive than this one, right? Because if this one had a reduction potential that was more positive, its electrons would not want to go here. They would want to stay here because this compound would want to be reduced, so it would keep its electrons. But this compound, as we see experimentally, gives its electrons to this one on the right, and by giving away its electrons, this compound itself is becoming oxidized, and in turn, it reduces this one. So, with that logic in mind, let's think about what we want this farthest compound on the right to have. Do we want this to have a high and positive E prime naught, or a low and negative one? And in my mind, I would think, well, we would want it to have a large positive E prime naught, because if it did, it really wants to be reduced, so it would steal the electrons from this one. If this one had a slightly more positive E than this one, that'd be great because it would steal its electrons. And same for this one. So going with that logic, this compound will have the least positive E prime naught, which out of these four choices would be this one. So X would be the farthest one. Then this compound would need to have the next more positive E prime naught, which in this case will be Z. Then the next more positive E prime naught will be Y. And then finally, the most positive E prime naught will be W. And that is how you will assemble this hypothetical electron transport chain. Okay? Hopefully this was helpful. If you have any questions, please email me or your IA or anyone and ask, and we'll be happy to help. Okay? Good luck studying.